Hey everyone, so we are going to start talking about determining limits involving infinity. So far we have talked about a couple of other ways to evaluate limits, and we're going to review that kind of looking through. This is actually, if you look at the beginning of your packet, one of the learning targets written there is 1.6. And so these are some of the learning targets that go along with it. So I can calculate the value of a limit algebraically using substitution. So if you think about that flow chart that we made in class, this is actually the first thing that we said we always do. If we're evaluating a limit at a specific value, then the first thing we do is substitution. If that doesn't work, then we need to try some of these other algebraic manipulations. So these other algebraic manipulations include factoring, multiplying by a conjugate, or eliminating the denominators. So that's the second part of what our flowchart was, right? If substitution didn't work, then we said, hey, can you do one of these? And now try to substitute. So now we're going to talk about this first big idea is what if none of these strategies work? So in other words, what happens if we aren't able to factor or do a conjugate or eliminate a denominator, or if we do and something is still wrong with it. So if none of our algebraic techniques for determining the value of a limit are successful, then the graph must have a vertical asymptote at that value. And we've talked a little bit about vertical asymptotes so far, where I gave you guys a graph and you had to describe the limits on either side, and we talked a little bit about what happens there. But now we're going to look more closely at what's happening when I give you, excuse me, when I give you a function instead of actually the graph. So here's another one of our learning targets, 1.14. So I can identify the locations of vertical asymptotes. I can analyze the behavior of a function near a vertical asymptote to determine the value of a limit. So this is what we're really going to be focusing on for the first part of the video. So let's talk a little bit about analyzing vertical asymptotes both symbolically and graphically. So we know that only rational functions can have vertical asymptotes. So a rational function will have a vertical asymptote at x values that make the denominator equal to 0. Remember that a rational function means it can be written as a ratio, right? Rational means ratio, which really just means fraction. So if we look at this one down here, we have f of x equals x plus 1 over x squared plus 3x plus 2. So the first thing we have to actually do before we can determine the vertical asymptotes is we have to factor the denominator. So this is x plus 1. And when I look at the denominator, what multiplies to 2 and adds to 3, that's x plus 1 times x plus 2. And we can actually see that this x plus 1 cancels, and we're left with 1 over x plus 2. So you have to be careful because it may look, if we only looked at the denominator, it may look like we actually have two vertical asymptotes. But we don't. We know that because that canceled, that x plus 1, this creates a hole at x equals negative 1. So be careful, that's not a vertical asymptote. It's actually a hole. So now we're going to take our denominator and set it equal to 0. So x plus 2 equals 0. That means that we have a vertical asymptote at x equals negative 2. Because if I plug negative 2 into this function, I'm going to get a 0 on the bottom, and that's a problem. All right, so again, be careful. Make sure you don't identify a hole as a vertical asymptote. Okay, now let's look at this graphically. So when a function has a vertical asymptote, the y values of the function are forced towards either positive infinity or negative infinity. right? We talked a lot about what happens on either side. It could either be shooting up to positive infinity or down to negative infinity, or they could both be up, both be down, could go like this, however, right? We know though that it's got to be one of those. Therefore, when we estimate a limit at the location of a vertical asymptote, the limit value will always be either positive infinity or negative infinity. So let's see what we mean by this. If we look at this graph, we can clearly see that there's a vertical asymptote at 0. And so if we want to look at the right and the left limits here, this would be my left-sided limit. So as x approaches 0 from the left of f of x, we can see that this graph is going down on the left side. That means that this limit is negative infinity. On the other side, this would be from the right. So as I approach 0 from the right, I can see that my vertical asymptote is being forced, or my function, excuse me, is being forced up on this side. That means that the right-sided limit is a positive infinity. Okay, let's move on to the next page. So determine the following limits using algebraic techniques. So the first thing we're going to do is we're going to look at this. We've got this rational function, f of x equals 3 over x plus 2 raised to the 4th power. So we can see that this is definitely a rational function. Anytime you have a variable in the denominator, we know that it's a rational function, okay? So what you need to think to yourself is, where is the vertical asymptote? So in this particular case, if we look at the denominator and set it equal to 0, we have a vertical asymptote at x equals negative 2. So what we know then, so therefore, hopefully you guys have seen that before, those 3 dots like that. Therefore, we know then that the limit must be either positive or negative infinity. Because if we look at where we're trying to evaluate this limit, all of those x values are approaching negative 2. We've got one from the left, one from the right, and then we've got the overall limit. But either way, since we're trying to evaluate a limit where there's a vertical asymptote, we know that the limit has to either be positive or negative infinity. So what we're going to do then is, if I'm approaching negative 2 from the left, then in my head what I'm kind of doing is I'm thinking negative 2.001. All right, and all I'm going to do then is just a little bit of sign analysis. So when I look at this function, the numerator is always positive because it's a 3, right? So I know that the numerator is always a positive number. When I look at the denominator, if I plug in a negative 2.001 and I add 2, I know that's going to be a really, really small negative number, but I'm raising it to the 4th power, which means even though it's negative, this denominator is going to end up being positive. So all I need to know then, positive over positive, means I'm going to have a positive infinity for my limit. Okay? Let's look at the next one then. So if I want to approach negative 2 from the right, in my head what I'm kind of thinking is negative 1.999. And again, because I'm approaching where there's a vertical asymptote, I know that it's got to either be positive or negative infinity. I just need to figure out which one. So my numerator is going to be a positive because it's always 3. And I'm going to look at my denominator. Excuse me. If I plug in negative 1.999, I'm going to and add 2, I'm going to get a super small positive number, and I'm going to raise it to the 4th power, which still means I'm going to get a really, really small positive number. Which means this limit, as I approach it from the right side, is also a positive infinity. Okay, then if I look at overall, what is my limit as x approaches -2? I need to be the same on the left side and the right side. So since these were both positive infinity, my overall limit is also positive infinity. All right, I just want to make sure that you guys are all clear on this really fast though. The limit is only positive or negative infinity when we're approaching that vertical asymptote. So for example, if I wanted to look here at the limit as x approaches 2 of f of x, I don't have 2 as a vertical asymptote. My vertical asymptote is -2. So all I would actually do here is try my original things here. I would actually plug this in. So I would get 3 over 2 plus 2 raised to the 4th. So that would be what? 3 over 4 to the 4th, which is going to be 3 over 256. So again, the limit's only positive or negative infinity when we're actually approaching that vertical asymptote. All right? So let's go ahead and do this example really quick. We can again see that it's a rational function. So we need to think to ourselves, where is the vertical asymptote? We can tell if we look at the denominator here and set it equal to 0, we have a vertical asymptote at x equals +1. And if I look at the limits that I'm trying to evaluate here, I can see that all of those limits are approaching 1. We've got the left, the right, and the overall, which means all of these limits are going to be either positive infinity or negative infinity, and then we know for the overall it needs to match, otherwise it does not exist. So I want you guys to think through a little bit of sign analysis, and I want you to see if you can figure out what are the values here. Are they positive infinity, negative infinity, does not exist, whatever's going on. So I want you guys to fill this out, okay? And I will check that in when I see you guys in class. We're going to do this next part together in class, so we're actually going to move on. I'm going to try not to make this a super long video. So let's move on to big idea number 2. How do we actually plug in positive and negative infinity? So we already know that that's not a thing, right? So that was the first thing on our flow chart actually, was are we plugging in a real value, a number? And if we said yes, we got to do all of our algebra-y things. Here, though, we can't actually plug in positive or negative infinity, so we can't actually substitute. Our first strategy is to try to substitute, though. The x values into the given function. However, in situations when x is approaching either positive or negative infinity, we need to rethink our substitution process because positive and negative infinity are not concrete numbers. They're not real numbers. They're ideas, right? So when we evaluate limits such as x approaching either positive or negative infinity, we are really examining the horizontal asymptotes. Of the function. So here's your learning target. Let's jump down to what this actually looks like. Hopefully end behavior sounds pretty familiar to you guys. But let's look at it graphically because we've kind of talked about that already. So if I want to do the limit as x approaches infinity of f of x, that means as my x values are getting bigger and bigger. So I can see that this right here is the piece I want to focus on. That's approaching this horizontal asymptote here at 1. Then if I look at x approaching negative infinity, I can see that that's this portion here that's also approaching 1. So we can see then, here's that horizontal asymptote. So on either side of my x values, I'm still approaching the asymptote. That's my end behavior. Okay? Then let's look here. We've got this, looks like almost a cubic function, I think. So the limit as x approaches infinity of f of x. So as x is getting bigger, I'm shooting up this way, and I'm going off to positive infinity. And as x is approaching negative infinity, my y values, my function values are getting bigger in the negative direction, so that's going to be a negative infinity. All right, so since infinity and negative infinity are very large numbers, we only need to examine the highest power of the function when we're evaluating. So this was graphically. Now we're moving on to algebraically. So what happens when I give you this actual function? How do you determine this without actually having to graph it? Okay? So what we're going to do is we're going to focus then on the highest powers of the function. So if I look here, the highest power in my numerator is this x to the sixth. So 5x to the sixth is going to be really important. And in my numerator, it's 3x to the seventh, which means if I look at my overall end behavior model, what I'm really focusing on is f of x equals 5x to the sixth over 3x to the seventh, which I can then simplify down, right? We can simplify some of those x's. It's 5 over 3x. And I'm actually going to go one step further, and I'm going to write this as 5 over 3 times 1 over x. And the reason I'm going to do that is because I know what the end behavior of 1 over x looks like. I know in my head, even with this 5/3 in front here, I still know what this graph looks like. This is my inverse function, and I've got a branch here, and I've got a branch here. So I know then that the limit as x approaches infinity is this horizontal asymptote, which is 0. And same thing when x approaches negative infinity, my overall limit is going to be 0 because that's my horizontal asymptote. So it's important to note that if the value of the limit as x approaches positive or negative infinity is a real number, so for example, if it's like 2, then the function must have a horizontal asymptote at that value. So if we ever say the limit of f of x as x approaches either positive or negative infinity equals some number, then that means there's a horizontal asymptote at that value. So here we said the limit as x approaches 0, or I'm sorry, the limit as x approaches infinity of f of x equals 0. That means this function has a horizontal asymptote at 0. Hopefully that makes sense. I feel like I'm kind of rambling a bit. I'm sorry. I don't feel well, you guys, so I'm doing my best here. Okay, moving on. Let's do a couple more examples and then I'm going to let you guys go. So when we look at this next one, we need to focus again on the highest powers. So in the numerator, that's my 5x to the 8th. And in the denominator, be careful, it's not written in order. Here's my 8x to the 6th. So for my end behavior model, I'm looking at f of x equals 5x to the 8th over 8x to the 6th. And when I simplify this down then, it becomes 5/8 x squared. So if I think about what that looks like, that's a parabola. So I know that I'm going to be something like this. I don't know exactly what's going on, but really what I care about is that it's a parabola and it's positive. And so I know what my end behavior is. As x approaches infinity, my parabola is approaching infinity, and as x approaches negative infinity, my parabola is also approaching positive infinity. All right, so what we're doing is we're using that end behavior to really model what's going on here. Let's really quickly look at this last one. So here's my highest power in the numerator and the denominator. So when I look at my end behavior model, it's 7x to the 7th over 3x to the 7th, which really simplifies down to 7 over 3. And so what we're looking at is we can see then that this is just a horizontal line at 7/3. That's actually my horizontal asymptote, which means that's my limit as x approaches infinity and negative infinity. we're going to do the 3 examples there in class along with this stuff at the bottom and the other thing we skipped. So please, if you had questions, please write them down. I know I kind of rambled a little bit and I spoke a little fast at some points. So ask questions if you've got them when I see you guys in class. Thanks for watching.